Hi, this is Glenn Dane from Ohio State University. Sorry I couldn't make it to the meeting. I did want to put one idea on the table and let you guys hopefully build on it and consider it and do with it as you will. And this is something I've been working through LIFT, Lightweight Innovations for Tomorrow, one of the Manufacturing USA institutes. Jane Cow and Alan Taub have also been instrumental in this process, and I think you'll see their influence through this. And what this is something that we like to call metamorphic manufacturing. I think you'll see what that means in a little bit. And let me just get right down into it, and I'll be very brief with this, and hopefully you can use this as something to build upon at the meeting or but here's what the big picture that we see is there have been three big waves in digital manufacturing, really two so far. The third one we see coming, and we think it's inevitable. Back in 1949, CNC machining began. It was largely in response to things going on at World War II. We needed to make airfoil shapes. Making them was very difficult. We had cams and all these fixed tools basically that allowed us to move milling machines around. And the great idea came forward that, boy, maybe we could put this with this emerging thing called computer technology. There was also some technology for moving gun turrets around that was used to control the milling machines. And that became CNC machining, and it's obvious to everybody where that is today. The next one is additive manufacturing. That really, you could see the groundswells of that before 1987, and it really started coming out in 1987, additive manufacturing. It's now what it is today. It's obvious to everybody, again, what this is. We can create shapes, and there's a lot of work going on to get the right materials and properties involved. And that's one of the largest growing areas we have right now. The third thing that's going on right now, or we think is going to happen, is what we call metamorphic manufacturing. And you know how metamorphic rock works. Basically, you're at fixed chemistry, fixed mass. You change the shape, you change the properties all at once. And this is a lot like what a blacksmith does. And we'll make that analogy in a moment. So here's what's happened in the past. We know blacksmiths could do amazing things 500 years ago. They could make blades with hard edges and soft cores. They could make incredibly intricate shapes, and they could do that with no more than the sensors that are in their eyes, their human strength, and a few simple tools. Well, we think that computer systems could do the same thing today even better. If you imagine you've got some kind of a system to put the shape into things. It could be a power hammer, it could be an English wheel, it could be something else. You can imagine putting interchangeable tools in there, much like we do right now. You could also imagine some kind of a heating system that could be applied with this. In this case, we imagine some little lasers that spit out of this. You could imagine some kind of sensors here that sense shape, temperature, and all that. This little horseshoe there becomes your workpiece, and this light-duty robot simply moves this around in this thing. This is a vision of what we call a robotic blacksmith, and we think this is something that could actually be done in a few years. It's not really so much the analytical research kind of problem that's typical, but instead what it really is a problem of synthesis and synthesizing together modeling and simulation, give this thing some ICME guts the way a blacksmith might have, developing machines, heating and cooling. You've got to integrate, certainly things like induction heating, flame heating, laser heating, all that is out there. There's a lot of room for sensors in this. You could imagine sensing shape, you could imagine sensing anisotropic material properties, and then also positioning is something that also needs to be sensed and controlled. And all of that can be integrated to make one system where basically this system here behaves like the blacksmith of old did, only you can do it with much greater power, much greater precision, much greater reproducibility. So this is what we think can be a revolution. Basically, this can be sustainable. Standard materials can be used, which is a big advantage over additive manufacturing because you have a big menu. Nothing is cut away, also makes it sustainable. You can have higher properties, as we metallurgists know wrought metals have the highest strength and toughness. We can use a range of materials. This is actually scalable to large sizes in a way that isn't available With additive manufacturing, they're usually talking about grams per hour. So you could usually imagine systems that are quite large to do this. Imagine power hammers and drop forge presses and so forth. We can use heat treatment and strain to augment and control properties locally. And the thing that really is big about this also is a blacksmith could never make something you'd put on an airplane, because blacksmith just can't be reproducible. Sometimes a blacksmith is hungover, has a bad day, whatever. We can be consistent and reproducible, and if you do this right, we can roll this back into standards. That's a big deal. And we also think this can be relatively affordable. Blacksmiths have been doing this for a long time, and a smart machine can work 24/7. And of course, there's all kinds of savings if you don't have to make dies and all this. And if we could do this, 400, 500 years ago, with just blacksmith-powered ingenuity, imagine what a robot could do today. So we've thought about this. We've thought about how to bring this forward. Again, it doesn't really look like a traditional research program. It's a matter of, figure it out. What do you have to do? Through LIFT, through the workforce division of LIFT, we've come up with a competition for U.S. students, which is described at roboticblacksmithing.org, basically to make these 3 shapes with one simple system. That system probably does look like something like a light-duty robot with a milling machine next to it. And in the particular case of this horseshoe, you could imagine using something like this, where you first take a mill, put a platen on one side that can go up and down and back and forth, have the base plate here, you can roll something here, take a sphere, turn that into something that looks like a hot dog. You could imagine incrementally hammering that down. You could imagine some kind of incremental roller system, again, just positioning that on the mill with the robot could do that. A few more banging steps, and before you know it, you've got something that really approximates that. And with a little ingenuity, you can imagine putting some other motions in, so you could make this and that with the same system. Basically, the robotic blacksmithing puts out a challenge for American students. Students defined broadly, they can be graduate students, undergraduates, to demonstrate they can make a system to make these parts out of plasticine to start. The year after that, there'll be another competition where we try to do this with soft metals, maybe not exactly the same shapes. Then after that, we're going to try to make systems that look like a full-on blacksmith, where we do heat treating and all the like. Where we're going, if you apply this to sheet, which is really the focus of this meeting, there's lots of things you can do. Jane is one of the experts in the world on incremental sheet forming this way. That can be done. There's other things. This is an English wheel. It's another approach. There's some work coming out of Germany, where you're starting to see robots with little squeezy things. There are also specialized tools for shrinking or stretching metals that can be used with sheet. Again, you can imagine dimensional sensors, temperature sensors to do things closed loop. This can also go to other shape classes like bars. Again, you could take something like a sphere and turn it into another shape with a kind of rolling technique. There's also other kinds of shaping techniques. There's lots of rooms for the equipment and all of that to go. We've put together a roadmap of how agile forming might look. And this is a little bit hard to read, but you see enablers here, and this is things like control, heating, understanding the robotics, machine learning. There's emerging processes that are coming up with this. You have to think about process selection and design. But again, there's all kinds of things you can do if you can really describe shape numerically, as we know well how to do, and then develop processes to drive things forward. So this is another little more graphical version that Jane put together that really deals with agile manufacturing more broadly. But the main part we're really trying to think about is this middle part for now, is how we take the old school blacksmith, replace his hammer and anvil with some kind of a tool, replace the heating dragon with some kind of other tool, and then you could imagine, again, a system that I think is the natural next wave of, excuse me, this thing stopped on me. Just had a little software glitch, poked the wrong part of my iPad. So you could imagine pulling these processes together and so forth. And again, we think that LIFT, the Manufacturing USA Institute on Lightweight Metals, is actually a good driver for this because it deals with a lot of the issues related to workforce synthesis, bringing together the community of companies, managing IP centrally, all of that can't be done very easily elsewhere. So as you develop a plan, think about LIFT as a possible way of doing this. One other thing that's really important in this is setting the right environment for research. And I still think, anyway, I'll let others reach their own conclusions, that the United States does not do a very good job in translational research. We do a very good job in early stage research, but not so good afterwards. And we've also been doing some studies on looking at what goes on with technology. This is just ISI work where you look at titanium additive manufacturing. We look at the fraction of publications in the U.S. That's on this axis over. That's over on this axis over here, where this is 100%. This all started basically in the U.S. And you can see as the number of publications rise, as you go from basic idea towards application, the fraction of work going in the U.S. goes from a high level down to a low level. And that's a trend that seems to be persistent and problematic for us as we really try to move things forward. We reduce, we tend to move out of it. An area I've been working in, impulse metal forming, does something very similar. This is a U.S. fraction. We've done a lot in the early 90s. Other parts of the world get involved. Number of publications rise. This isn't a huge area, but we're at about 35 publications a year. And again, the U.S. is under 20% on average of the publications that come out on an annual basis. Machine learning, we think, will be an important part of this. Again, this is an area that was largely founded in the U.S. back here in the early 90s when there were just a few papers, under 10 per year. We dominated the field in the U.S. And as you get to present day, you're up around 70 publications. And this is machine learning plus process. In that, we're up about 60 papers per year. And again, the U.S. fraction of that input is down below about 30% on average. So that's another part of the problem that we think is fairly important. So I'm going to try to stay brief with this. I've got two requests for you. Number one, I wanted to pitch to this group the contest we have going on, and we have a good website at roboticblacksmithing.org, which has all of the contest details and so forth. Please encourage your students to be part of it. And if you know others that would like to be part of it, there's at least $50,000 of prizes, cash money being given out in April. It's not too late at all to become deeply engaged, and we would love to see your team be part of this. The other probably more important thing is as you develop the road mapping you're doing with the NIST road mapping with chain, please think about this approach of what we call metamorphic manufacturing as it applies particularly to sheet. Again, we want to set the table so the U.S. can do some good things in here. We think the LIFT Institute is actually a great way to coordinate all of this work. Think about the technical elements, the funding elements, how you'd collaborate, how you do IP, and then anything else that would contribute to this vision. I think what you're doing today is probably a perfect venue for that. And I'll stop there. Thanks very much for considering this, and my apologies for not being able to make it.